equations, general steps to solve linear equations, how to verify the correctness of a solution, and finally how to verify the solution or the root graphically. Let us have a look at a few examples of linear equations. Here we have three linear equations, and generally such equations are the simplest type of equations to solve. Also, a linear equation is an equation where the power or the exponent of the variable or the unknown is 1. Note these three equations, linear equations. The unknown in all three cases is x, and the exponent in this case is plus 1. And with no term do we have an exponent of the unknown bigger or other than plus 1. This type of equation, the linear equation, is also known as an equation of the first degree. And we will learn how to find what value of x makes both sides of the given linear equation true. And also, there is always at most one solution or root, which is another way of describing a solution, for a linear equation. So, a linear equation can have either no solution or no root, or exactly one root, but never more than one root. Let's consider the following. From the solution to an equation, in this case x equal to 3 for example, one can construct a linear equation. For example, we can multiply both sides of such a solution. By the way, a solution is also in the form of an equation by 3, and in this case we generate the equation 3x is equal to 9. Then we can decide to subtract 4 from both sides of the equation, and we generate the equation 3x minus 4 is equal to 4 less, of course, than 9, which is 5. After this, we can multiply both sides of the equation with 5 and generate this particular equation as you can see on the screen. And finally, we can decide to divide both sides of the equation by 2 and generate this particular equation. Now this equation as it is given on the screen is also a linear equation. So if we start on the right hand side with the equation and try to solve this, we have to apply the reverse process to the above. And also in this case the first step would then be to multiply by 2 on both sides of the equation to get rid of the 2 in the denominator position. Remember, previously we divided by 2, so here we multiply by 2. So it's like the inverse operation to get the equation as indicated. 5 times 3x minus 4 is equal to 25. Now, on both sides of the equation we now divide by 5 instead of multiplying as before to get rid of the 5. So in this case we generate the equation 3x minus 4 is equal to 5. To get rid of the minus 4 on the left hand side, we add 4 both sides of the equation, and in this case we generate the equation 3x is equal to 9. To get rid of the coefficient of the unknown x on the left hand side of the equation, we now divide through by 3 to get the solution, in this case x is equal to 3. This process is also referred to as making x the subject of the formula. In this case x was the only unknown, so in the end we generate a constant for the unknown, which of course in this case will also represent the solution or the root for the linear equation that we started out with in such a case. There are in general 7 steps to consider when one solves a linear equation. Let us consider these steps. Step number 1 is, if there are any fractions on the left hand side or the right hand side of such an equation, we have to multiply all the terms on both sides by the lowest common multiple of such denominators. Secondly, one has to remove brackets wherever it is possible. That is on the left and the right hand side of a given linear equation. Next, we have to transfer the terms containing the variable or unknown to the left hand side of the equation if needed. Now this process is called transposing the variable to the left hand side, and if we have an addition on the right hand side or a plus, it becomes a negative when transposing it to the left, and vice versa. If it's a negative, it becomes a plus. Also, we have to transfer the other terms, in other words the terms not containing the unknown or the variable, to the right hand side of the equation or equations in the same way by transposing and changing appropriately the sign in such a process. The next step, number 5, will be to simplify both sides of the equation where possible. And then finally, we have to divide by the coefficient of the unknown that is on the left hand side of the equation now. And finally, we have to test the resultant equation, which represents a solution, for correctness. And this process we will discuss in subsequent slides. We will now demonstrate the application of the 7 general steps to solve a linear equation. Let us consider this particular example of a linear equation where we have to solve for the unknown x. The first step would be to multiply each term that is on the left and the right hand side of the equation by the lowest common multiple of the denominators that appear, of course, in this equation. Now here we're looking for the lowest common multiple of 4, 2, 3 and 6, and of course that is equal to 12. So multiplying on the left and the right hand side of this equation by 12, we have to then generate the resultant terms. First of all, if we multiply 12 into this bracket, we have to multiply with x divided by 4, this particular term inside the bracket, and we have 3x as a result. Multiplying 3 over 2 by 12, we get 18, that is 6 times 3. Also, if we multiply x over 3 by 12, we get 4x with a negative intact in this case. So that's the left hand side of the equation. Do the same on the right hand side, multiply by 12, we get 24 minus, and if we multiply this particular fraction, 2x minus 3 divided by 6 by 12, we get, in this case, 2 times 2x minus 3. So that's the first step. Second step will be to remove the brackets wherever they appear in the resultant equation. So that means we have to multiply the 3 into this bracket and also the minus 2 into this bracket. Using the distributive property, we multiply out and we get 9x. 3 times 18 is 54, and in this case minus 2 times 2x, which is minus 4x, and minus 2 times minus 3 is plus 6. The next step would be to then transpose and change appropriately the signs of all terms containing the unknown x in this case. That must move to the left hand side. So all terms containing x to the left hand side, this minus 4x must be moved then to become plus 4x on the other side. And also terms independent of the unknown x must be moved to the right hand side. So the plus 54 becomes minus 54 in such a case. So constants on the right, all terms containing the unknown on the left. That is what we're aiming for in these steps. The next step would be to simplify the left and the right hand side by consolidating the terms, and we have the resultant equation 9x is equal to minus 24. Please check that. After this, we have to get rid of the coefficient here in front of the unknown x in order to make x the subject of the formula or to generate the solution for such a linear equation. So in this case we have to divide both sides by the coefficient of the unknown, in this case 9, and we generate a solution x is equal to minus 24 over 9, and if we simplify this particular rational number we have minus 8 over 3, or it can also be written as minus 2 and 2/3. Now that is the solution process of the given linear equation. The final step would be to check whether this answer is indeed correct. How do we do that? Well, we have to substitute this particular value, minus 8 over 3 for x, into the original equation on both sides of this equation. Wherever x appear, we must replace it by this particular value, minus 8 over 3, and check that the left-hand side tallies with the right-hand side, that the two values are indeed equal for the left and the right-hand side. So here we go. Test the correctness of the solution, substitute the value into both sides of the original equation and check. And this is something that you can also then verify. As can be seen on the screen, this indeed represents the correct solution for the given linear equation. Let us have a look to see what the solution of the linear equation that we saw in the previous screen looks like graphically. Here we have this particular linear equation, and we found the solution of this equation to be x is equal to minus 8 over 3 or minus 2 and 2/3. If we graph this particular solution, then we see we have a straight line, a vertical line, blue on the screen, parallel to the y-axis, and it has a point of intersection with the x-axis at the point with coordinates minus 2 and 2/3 and 0. Note that we have written this particular minus 2 and 2/3 accurate to 2 decimal places, as can be seen on the screen. Now, this then represents the solution for the particular linear equation. That is, where x is equal to minus 8 over 3, a vertical line as indicated. In general, the solution process of any linear equation can be reduced to a solution of the form x is equal to a constant, which we indicate by k, and of course this constant will always be a real number. So a linear equation of this particular form, again, if you represent this graphically, will be a straight line parallel to the y-axis. Here we see a specific case of such a solution, and this particular k value is the root for the given linear equation. And furthermore, the point with coordinates k and 0 is the point of intersection of this particular solution, x equal to k, and y is equal to 0, or the x-axis. Here again we see an example of exactly where the point of intersection with the x-axis lie. The point of intersection of the root or the solution as an equation, in this case x equal to minus 8 over 3, and the x-axis will be exactly the point corresponding to what we've just described. We will now consider an example where we will solve a more complex linear equation. Here we have the problem. We have to solve for the unknown x given this particular equation, which turns out to be linear as well. Since we can factorize the denominators in this case, and if you're not too familiar with the factorization of trinomials and difference of squares in this case, I suggest that you look at one of the 2 videos on basic algebra, which forms part of the grade 10 video series. In this case, we have to multiply both sides of the given equation by the lowest common multiple, which in our case will be the product of the 3 linear factors as indicated on the screen. And if we multiply the first particular expression here with the lowest common multiple as indicated, then we're left with 2x plus 3 above the line. In the second case, we're left with plus 3x plus 5. Note that the negative has changed to a plus because in the lowest common multiple we have utilized the 2x minus 3, which is just the negative of this particular factor. Since we have multiplied then by a negative, we have to compensate and have a plus in front in such a case. On the right hand side of the equation, multiplying by this LCM, we have above the line the expression 2x minus 3. Now we're back to where we were at the previous slide when we solved the linear equation, and we continue with these steps that we saw earlier in order to solve such a linear equation. That is, we consolidate on the left hand side all the terms containing the unknown x, and on the right hand side we have all the constant terms. In other words, we migrate to the left and to the right the terms as indicated before. Note that in this case, since we have these factors 3x plus 5 and 2x minus 3 as well as 2x plus 3 in the denominator positions, we have that x immediately cannot assume the value minus 5 over 3, neither can it be either plus or minus 3 over 2, because then it will result in division by 0. So we have some restrictions on the values for the unknown x already. Continuing with the process of solving, we consolidate the left hand side and the right hand side of this linear equation, and we have 3x is equal to minus 11, and then as before we get rid of the coefficient of the unknown by dividing through by 3, and we have the solution in this case given as x is equal to minus 11 over 3. And I challenge you to use your calculator to test the correctness of the solution. In other words, you have to substitute minus 11 over 3 on the left hand side everywhere where we have the unknown x, as well as on the right hand side in such a case. You should be ready now to try your hand at solving some of the linear equations that we have in tutorial number 1. Let's have a look at these particular problems. We have to apply now some or all of the general steps discussed earlier, where applicable of course, to solve the following linear equations. In each case you have to test whether the solution is in fact the correct one. Here we have 4 problems that you can try in this regard. At this stage I suggest that you pause the video, do tutorial 1, and then come back and view the solutions. Let us have a look at the solutions for tutorial 1. In the first problem we have to solve for the unknown x and test the solution. Here we have the linear equation, and the first step in this case will be to remove the brackets, both sides of this equation, by multiplying the 10 and the minus 1 into the bracket. In the first instance on the left we get 10x plus 10, multiplying the 10 with x and 1, and on the right hand side clearly the minus 1 multiplied into the bracket has the effect of changing the signs of the terms inside the brackets on the right hand side. After this we consolidate and transpose the unknown to the left and the constants to the right, as we did before. Just note the change in sign, and then we have the equation 12x is equal to minus 4, once we have simplified both sides of the equation. Dividing through by the coefficient of the unknown on the left hand side, we're left with the solution in this case, x is equal to minus a third. Just check that. Of course, we need to check whether this solution is in fact the correct one by substituting the value x equal to minus a third into the original equation, or the one that we have started out with, and check whether the left hand side gives you the same value as the right hand side. And this you can check by yourself and just verify that on both sides of the equation we have the same value. Thus x equal to minus a third is indeed a solution or a root for this particular given linear equation. The second tutorial problem is very much similar to the first one. Here we have the equation, the linear equation, and we have to solve this equation for the unknown x and test the solution. Again, we multiply both sides of this equation by the lowest common denominator, which is the lowest common multiple of 2 and 3 and 6. Of course, that is just 6. So in doing that, multiplying the 6 with the 3 over 2, we have 3 times 3, which is 9. And so we multiply through, and we get minus 4 here. If you multiply minus 2/3 with the 6, of course, you get 2 times minus 2, which is minus 4x. And on the right hand side, the same. Multiplying the 2 with 6, we get a 12. And also multiplying this particular algebraic expression, we get minus, in brackets, 4x minus 3. Remember, the negative here means it's in front of the expression 4x minus 3, so you must use the bracket in that case. Okay, so the next step would obviously be to remove the brackets on the left and the right hand side of the linear equation. That we do by multiplying the coefficients in front of the bracket into the bracket, and in this case multiplying by 9, we get 9x plus 27. Minus 4x remains the same on the left. Then on the right hand side, 12. The minus 1 multiplied with the expression 4x minus 3 inside the bracket just means that we change the sign of the terms as we did on the screen. Minus 4x plus 3 instead of 4x minus 3. The next step would be to move all the unknown terms containing the unknown x to the left hand side and the constant terms to the right hand side, that is transposing to the respective sides and also changing the signs appropriately if you do so. So 27 becomes minus 27 on the right, and for example minus 4x on the right becomes plus 4x on the left hand side. Then we consolidate the like terms on the left and the right, we simplify, and we end up with the linear equation 9x is equal to minus 12, which if we divide through both sides of the equation by 9 to get rid of this particular coefficient of x, we have x equal to minus 4 over 3. And clearly again, we have to test this for correctness. If we take x equal to minus 4 over 3, substitute it into the original equation, both on the left hand side and the right hand side, in the place where we have positions where we have x, then using your calculator or otherwise you can check and verify that the left hand side and the right hand side indeed agree. So this in fact is a root or a solution for the given equation that we started out with. In problem 3 of tutorial 1, we have a similar situation, a linear equation to solve for the unknown y in this case, and we need to test the solution for correctness. In this case, we choose to first multiply the coefficients of the brackets on the left hand side of this equation into the brackets, and after that multiply through on the left and the right by the lowest common denominator. Note that in this case we have denominators 4, 3, 2 and 6, and the lowest common denominator clearly will be 36 in such a case. So multiplying 1/4 into the brackets with the expression y minus 5, we have y over 4 minus 5 over 4. Similarly, if we multiply minus 2/3 with y over 3 and 5 over 2 respectively, we end up in this case with minus 2y over 9 and minus 5 over 3. Note, 2's will cancel. We have minus 5 over 3 as the coefficient or the term in such a case. Plus y over 6, our other term, is equal to 0. We start then with this particular linear equation and multiplying through by the lowest common denominator both on the left hand side and the right hand side, we end up with this particular expression on the left hand side. Just check that. Note, 0 times any number is 0, so the right hand side remains 0 if you multiply by 36. Next we have to move all the terms containing the unknown y to the left hand side and constant terms to the right hand side as before, and take note of these change in signs if you transpose in this way. consolidate, simplify on the right hand side, and on the left hand side we end up with the equation again. 7y is equal to 105. Divide through by 7, both sides of the equation, end with the solution in this case, or the root, y is equal to 15. And again, using your calculator or otherwise, check whether if you substitute y equal to 15 into the original equation, whether the left hand side is equal to 0, or whether the left hand side then agrees with the right hand side, which was 0 to start out with. In the fourth and final problem of tutorial 1, we're given again an equation to solve and to test the solution. In this case, it's slightly more complicated, since we first have to factorize the denominators, very similar to the example we had during the lesson. And in this case, you need to be familiar with the way of factorizing a trinomial and difference of squares. And if you're familiar with that, you should agree with this particular way of factorizing the denominators, both on the left hand side and the right hand side. The next step would be to find the lowest common denominator, which is of course in this case the lowest common multiple of the components, the factor components of the denominators as we see them, both on the left hand side and the right hand side. In this case it's the product of the three linear factors as indicated on the screen. Multiplying through by this particular product of linear factors, both on the left hand side and the right hand side, we will retain the integrity of this equation. In other words, the balance will remain the same, and we will cancel with the relevant factors below the line. And if you multiply the first term on the left hand side with the LCD, we remain above the line with 4x plus 3, the one factor that was not part of this denominator. And similarly, for the second term, we will remain with 6x plus 5 above the line. And on the right hand side, if we multiply by the LCD, we remain above the line with the expression 4x minus 3. Now this then is very similar to what we had before, a linear equation where we need to consolidate by transposing and changing the signs. Send all the terms containing the unknown x to the left hand side, send all the constant terms to the right hand side, take note of the change in signs, and simplify. We end up with the equation 6x is equal to minus 11, and if we divide through by the constant or the coefficient of x again, namely 6, then we have the suggested solution for the original equation, in this case x is equal to minus 11 over 6. Clearly, we have to check this for correctness, and also note that since we are dividing by these factors, x cannot assume the value minus 3 over 4 or plus 3 over 4, neither can x assume the value minus 5 divided by 6. But in this case, the suggested solution is x equal to minus 11 over 6. And checking that by substituting this value into the original equation everywhere where we have an x, then we can see that the left hand side indeed agrees with the right hand side as before. This is a challenge. Use your calculator, and in fact we have found the solution of this particular equation that was given. In lesson 2 of this video, our discussions center around solving quadratic equations. Let us have a look at the outcomes for lesson 2. In this lesson, we will focus on examples of quadratic equations, the standard form of a quadratic equation, zero products, general steps to solve quadratic equations, and finally, different formats of quadratic equations. Let us start by considering examples of quadratic equations. First, a few general remarks. A quadratic equation is an equation where the power of the variable or the exponent of the variable is at most 2. In other words, we can have constant terms where the exponent of the variable is 0, or we can have linear terms where the exponent is 1, and we can also have a term containing the unknown with the exponent 2. Such an equation is called an equation of the second degree. Note that in this particular lesson, we will only solve quadratic equations by means of factorization. Also, quadratic equations has at most two solutions or roots. So, we may find that we have no solution for a quadratic equation from the real number system, that is, or one solution or two solutions, but we cannot get more than two solutions in such a case. Here we have three examples of quadratic equations. In example number 1, we have a term which contains the unknown to the power 2, another term where the exponent or the power of the unknown x is 1, and on the right hand side we have a constant term, of course, where the exponent of the unknown x is 0. We can also have a quadratic equation in the format as indicated in example number 2, since if we multiply through on the left and the right hand side of this particular equation with the expression 3x plus 1, we end up with an equation where if we simplify the right hand side by expanding, multiplying 4x into the expression 3x plus 1, we generate a term where the exponent of the unknown will be 2. So this in fact represents a quadratic equation, but clearly in this case we have a restriction for the value of x, namely x cannot be equal to minus a third, otherwise we will have division by 0. And in the third example, there is another way of representing a quadratic equation. So you can mix the terms on the left and the right, having the exponent 1, 2, or a constant term for the unknown x in such a case. We now consider the standard form of a quadratic equation. The standard form of a quadratic equation is given by the equation as indicated on the screen, namely ax squared plus bx plus c on the left hand side is equal to 0 on the right hand side. Now in this case, x of course is the unknown or the variable for this particular equation, where a is the coefficient of x squared, b is the coefficient of x, and c is independent of the variable x, also known as the constant of such an equation. Now the unknowns a, b and c, the unknown constants a, b and c represents real numbers. They can assume any real value, and a in general will not be equal to 0. Since if a is equal to 0, this quadratic term in this particular equation will become 0, and it reduces to a standard linear equation as such. So a, b and c are real numbers, and a generally not equal to 0. Before we discuss a method for solving quadratic equations, we first consider the zero products. Well, if we have two real numbers, say a and b, and we have that the product of the two real numbers, a times b, is equal to 0, then either the first factor a must be 0 or the second factor b must be 0. That is for real numbers. So we have that if a is equal to 0 in such a case, then b may assume any real value, also 0 for that matter. If the product of two real numbers in such a case, a times b is equal to 0, and we know that the factor a is not equal to 0, then obviously it implies that the factor b must be 0. Vice versa, if the product is 0 and you know that the right hand side factor b is not equal to 0, then it immediately implies that the left hand side factor a must be 0. So, in general, we can inductively extend this particular result and say that if the product of two or more factors is equal to 0, that is, if the factors represent real numbers, then at least one of the factors is 0. And this we can illustrate with an example. For example, let's have a look at the product of the three factors equal to 0 in this case, and we know that one of them, the first one, is not equal to 0, then immediately it implies either the second factor or the third factor must be equal to 0. And of course, then we can solve in such case for the possible values for x in such a case. We will now demonstrate the general steps that apply when one solves a quadratic equation. Let's have a look at this particular quadratic equation, and we have to solve for the unknown x. And in this case we will apply factorization. So the first step is then to rearrange the equation, in other words to write the equation in the standard form as discussed in the previous slide. Step number 2 will be to factorize the trinomial on the left hand side of this particular equation. And you should be familiar with this particular process. So we have the two linear factors. If we factorize 3x minus 2 multiplied with 2x minus 3, and the 0 must be on the right hand side. Next step is to apply what we have discussed in the previous slide, namely the product of two factors equal to 0 implies either the one factor is 0 or the other factor is 0. And from these particular cases we consider and solve to find the possible values of x, which then of course will represent the possible solutions for the original quadratic equation. In this case, x is equal to 2/3 or x is equal to 3/2. Note, we can never use the AND in this position. It's either the one case or the other case, according to what we have discussed. Now, the last step, or the final step, would be to test the correctness for each possible solution. And here you can use your calculator or otherwise substitute each of the two values individually into the original equation and check separately whether they qualify as a root or a solution. In other words, whether the left hand side and the right hand side agrees when we substitute these values independently. In some cases, the equation to be solved might not look like quadratic at first glance at all. In other words, equations may be in disguise. So let's have a look at three cases of such a particular disguised quadratic equation. Case number 1. Here we have an equation which really doesn't look like a quadratic to start out with. But if we have the unknown or the variable x appearing in the numerator position for each term, then you will see, in fact, that this is indeed a quadratic equation. So in this case, to facilitate, to rewrite this in the standard form, we have to multiply through both sides, left and right, with the unknown x. And in such a case, we generate, as you can see, the equation ax squared plus bx minus c is equal to 0, which clearly is a quadratic equation. But note, in this case, we immediately have a restriction for the possible values for the unknown or variable x, namely x cannot be equal to 0, since we have x appearing in the denominator position. Another case where the quadratic may be disguised, where we have the quadratic expression below the line. And in such a case we multiply across. Remember, c is the same as c divided by 1. Cross multiplication gives us the constant c times this quadratic expression is equal to 1. And rearranging, we can see in its standard form there's a quadratic term with the coefficient ac, a linear term with the coefficient bc, and a constant term, in this case equal to 0. So in fact, this is just another way of representing a quadratic equation. In this case, however, we cannot have the expression ax squared plus bx assuming the value 0, and that results after factorization, you know, that x cannot be equal to 0 or x cannot be equal to minus b over a either. If we solve this particular product x times ax plus b is equal to 0, we have two specific values which the x or the variable may not assume in such a case. In the third case, we have a different type of equation which also represents a quadratic equation with a restricted value, possible value for the unknown or the variable x. The square root of ax plus b is equal to cx. If we square both sides of this equation, then we have the equation ax plus b is equal to c squared x squared. we square the square root, it disappears, and we just have the expression ax plus b. On the right hand side, of course, if you square and apply your exponent rules, we have, in this case, the expression c squared times x squared. Now, rearranging this equation, again, we have a quadratic term with a constant or the coefficient c squared, a linear term with coefficient minus a, and a constant term if we rearrange in standard form for the quadratic equation. So really it does represent a quadratic equation, but in this case, be careful, we have to insist on ax plus b to assume positive real values or 0, since the square root of a negative number does not exist. So there's a restriction on the possible values then for, in this case, the variable or unknown x in such a case. In the first example that we consider, we have to solve for the unknown x given the quadratic equation as indicated on the screen. Now the first step would be to write it in standard form, 0 on the right, the expression on the left, and to factorize the trinomial on the left hand side of this equation. This gives us the factors 2x plus 3 and x minus 4 multiplied together is equal to 0, and as discussed before, either the first factor must be 0 or the second, which we write next, and this leads us to the possible solutions for the unknown x, namely x equal to minus 3 over 2 or x equal to 4. Just check that. To verify that these are both solutions or only one of them is a solution, we have to substitute both values into the original equation and check that they satisfy, both satisfy the equation. And in fact that is the case. If you substitute minus 3 over 2 into this particular quadratic equation that we started out with, we get the right hand side is equal to the left hand side, or it satisfies this equation. And similarly, if we substitute x equal to 4 into that quadratic equation, it also satisfies the equation. So we can conclude then in both x equal to minus 3 over 2 and also x equal to 4 are solutions for the given quadratic equation. Let us now also look at the graphical interpretation of the solution for example 1 that we have considered. We have showed algebraically that the solution for this particular quadratic equation is given by x is equal to minus 3 over 2 and also by x is equal to 4. We have two solutions in this case. Now let's consider the graphs of the parabola and the line defined respectively by this particular left hand side of this equation, the expression 2x squared minus 5x, and the right hand side y is equal to 12. In such a case, clearly, we have a parabola as indicated in blue. If you graph the function defined by this particular equation, y is equal to 2x squared minus 5x, and if you graph the function defined by the equation y is equal to 12, the constant function, we have the red graph, a line parallel to the x-axis, which intercepts the y-axis at y equal to 12. Now what we're really looking for is where will the output values be the same on the left and the right if we substitute values for x. In other words, these two x values as solutions for this equation are the two input values which will result in the same outputs on the left and the right of this particular equation. That is the algebraic way of viewing it, but the graphical interpretation is exactly what we have represented here on the screen. But if we consider this from a set theoretical point of view, we can see that the one graph, that is a parabola, is just a set of all ordered pairs or points on the Cartesian plane xy, which satisfy y is equal to 2x squared minus 5x. That's the left hand side of the original equation. So this graph will intersect or have a particular point in common with the graph or the set of points or the pairs xy which satisfy y is equal to 12, which is the right hand side of the original equation, where we have these two particular points. You can see the points of intersection right there. This is basically what we have determined. It occurs when x assumes either the value minus 3 over 2 or x is equal to 4. Corresponding to both of those, we have the same output value or the y value, namely 12, as was requested if we want to solve this particular equation that we started out with. So, the y-coordinates then of the parabola and the straight line are equal when we have these root values, or the values for the unknown x, which in fact represents the solution for the original equation, namely x equal to minus 3 over 2 and x equal to 4. Whenever we have those x values, we have the points of intersection of the two graphs as indicated. In example 2, one has to be careful, since here we have an equation which at first does not look like a quadratic equation. We have to solve for the unknown x as before. So the first step would be to square both sides of the equation. But also note that the left-hand side is the square root of 14 minus 5x, the positive square root. So it immediately means that since the right-hand side consists of x only, that x cannot be negative. It's either 0 or positive. So bear that in mind. Squaring both sides, we have 14 minus 5x is equal to x squared. Rearranging into the standard form for the quadratic equation, we have x squared plus 5x minus 14 is equal to 0. Then do the factorization of the trinomial on the left-hand side. We have the product of x plus 7 and x minus 2 is equal to 0. By our previous discussions, we have either x plus 7 is equal to 0 or x minus 2 is equal to 0 for the next step in this solution process. Now, it means really that the unknown x may either be minus 7 or it may be x equal to 2. Now, what we have discussed to start out with, this cannot be a solution because remember x must be either greater or equal to 0. Since the left-hand side is always positive, we're only considering the positive square root. We had a negative in front, of course, and it would be the negative square root, but it is not the case. So the only possible solution really will be x equal to 2, and we can even check that. Substitute minus 7 into the original equation on the left-hand side, we have the square root of 49. Okay? And of course, the right-hand side, if you substitute minus 7, we can see that the positive is never equal to a negative. So, in this case, x equal to 2 is the only solution, only one solution in this case, for this particular quadratic equation that we started out with. We will again consider the graphical solution for example 2. Remember that we have showed algebraically that the quadratic equation as indicated on the screen in example 2 has x equal to 2 as a solution, but that x equal to minus 7 is not a solution. Well, we will consider the graphs of one branch of the parabola defined by this particular expression or this equation, and the straight line defined by y is equal to x. In other words, we look at the left-hand side expression and look at the function defined by this expression, and also the right-hand side expression and the function defined by it, and graph both of those functions simultaneously on the Cartesian plane. Note that the branch defined by the negative square root is excluded. It's only the positive square root that we consider in this case. If we do that, then we have this particular graph. Can you see it's a parabola on its side? This part is excluded. In other words, the negative square root of 14 minus 5x as the defining expression for a function to be graphed. We only graph the one branch as indicated in blue. Also, y is equal to x, we graph that, that's the red graph, and in this case we can see that this would have been a solution had we included the negative square root of 14 minus 5x as well. But since it's not, we cannot consider this particular point of intersection of the two graphs as a solution for the original quadratic equation. Only the one point of intersection is valid, and therefore we can see that x equal to 2 is the only solution for the quadratic equation, and in this case the point of intersection would be x equal to 2, and if you substitute the value, of course you get y equal to 2 as well. And it is really clear from the graphs that x equal to 2 is the only solution, and that x equal to minus 7 is not a solution in this case. In the third and final example of solving quadratic equations, we consider the following quadratic equation that we have to solve again for the unknown x. The first step in this case would be to multiply through by the variable or unknown x on the left and the right hand side in order to write this particular quadratic equation in its standard form. So we have x times x minus 3 is equal to 28 on the right hand side. This, of course, after simplification and rearrangement, we have a standard quadratic equation, namely x squared minus 3x minus 28 is equal to 0. Note that x cannot be equal to 0. That is the exclusion for the possible value for x immediately. If we factorize the left hand side again as before, the trinomial, we get x minus 7 multiplied with x plus 4 is equal to 0. Product of two factors equal to 0 means either the one is 0 or the other is 0, and this means we have two possible values for the solution for the original equation, namely x is equal to 7 or x is equal to minus 4. Now, which of these two values qualify as a root, both, or only one, or none? That we have to check by substituting the values individually into the original equation and check whether in fact we have in both cases a root, whether it satisfies the equation, whether the left hand side is the same as the right hand side once we substitute. And indeed, both of these qualify as roots or solutions for the equation, and thus we have solved this particular quadratic equation algebraically. Again, looking at the graphical solution for example 3, we had algebraically that x equal to 7 and also x equal to minus 4 represented solutions or roots for the given quadratic equation. Now what we have to do now is to graph the hyperbola defined by the expression y is equal to, or the equation y is equal to 28 divided by x, that is the right hand side of the original equation, and the straight line defined by y is equal to x minus 3, that's the left hand side of the original equation. We have to graph these simultaneously on the Cartesian plane, and we consider the points of intersection. And as expected, when x is equal to 7 and when x is equal to minus 4, we have the points of intersection with corresponding y values. In this case, y is equal to 4 and y is equal to minus 7 respectively. But for those particular x values, if we calculate the left hand side and the right hand side, we'll have the same value in such a case. And this then makes it clear from the graphs that y x equal to 7 and x equal to minus 4 are both solutions or roots for the original quadratic equation. I think you should be ready now to tackle tutorial 2, where you have to solve a number of quadratic equations. Here we have the problems, 3 of them. Solve the following quadratic equations and test the correctness of each of these solutions. At this stage, I suggest that you pause this video and do tutorial 2 and then come back and view the solutions. Let us have a look at the solution for problem 1 of tutorial 2. In this case, we had to solve the given quadratic equation and test for correctness the solutions that we obtain. Now, as before, we rearranged the given quadratic equation in its standard form, 0 on the right, quadratic expression on the left, to the trinomial factorization. Check that. We have the factor 7x minus 2 multiplied with 2x plus 3 is equal to 0, and then either the one factor or the other factor equal to 0 gives us the two possible values for the roots of this particular equation, namely x equal to 2 over 7 or x equal to minus 3 over 2. And again, check with your calculator and you'll see that both these x values substituted into the original equation gives us in fact agreement between the left hand side and the right hand side. In other words, they satisfy the equation. In problem 2 of tutorial 2, we have a quadratic equation in disguised form, so we have to square both sides of this given equation in order to standardize this particular equation as a quadratic equation. So in doing that, we have on the left hand side x minus 2, the right hand side, if we square, we have 2 minus x all to the power 2. Expanding the right hand side, we have then the equation x minus 2 is equal to 4 minus 4x plus x squared. Rearranging this into the standard form for the quadratic equation, we apply then next the trinomial factorization on the left hand side, and we have the product of the factors, linear factors x minus 2 and x minus 3 is equal to 0. Which of course, if you consider them independently and solve, we get x equal to 2 or x equal to 3 are the possible solutions for the original quadratic equation. Now, in this case, we must test both solutions to make sure that they qualify as a root for the original equation. So if we check, for example, x equal to 2, substitute that into the original equation, we have the left hand side is equal to 0, the square root of 0 is 0, and the right hand side, in this case, will be 0 as well. So x equal to 2 is indeed a solution. Whereas if we substitute x equal to 3 in the original equation on the left hand side, we have the square root of 1 is 1, on the right hand side we have 2 minus 3 is minus 1. So 1 is not equal to minus 1. So x equal to 3 does not satisfy the original equation. So it's not a solution in this particular case. So the only solution then will be x equal to 2 in this particular problem. In the third and final problem of tutorial 2, we have to solve this given equation, which turns out to be a quadratic equation. And we have to test for the correctness of the solutions as well. Now we multiply cross multiplication. Since x is x over 1, we have here x times x plus 2 is equal to 15 times 1, or just 15, and that gives us the standard form of the quadratic equation, namely x squared plus 2x minus 15 is equal to 0. Now if we apply the trinomial factorization on the left as before, we have the product of the two linear factors, x plus 5 and x minus 3 is equal to 0, which means either the one factor or the other factor is 0, which gives us the two possible values for the roots of this particular equation, namely x equal to minus 5 or x equal to 3. Now if we substitute both of those independently into the original equation, we see that in both cases these values will satisfy the original equation. The left hand side is equal to the right hand side, and hence we can say that both x equal to minus 5 and x equal to 3 are solutions for the quadratic equation in problem 3 of tutorial 2. In lesson 3 of this video, the focus will be on solving simultaneous linear equations. Let us have a look at the outcomes for lesson 3. In this lesson, we will focus on the meaning of solving a system of linear equations in two unknowns. That is, solving a number of linear equations simultaneously. We will also consider solving such a system graphically by means of the so-called substitution method, and finally by means of the elimination method. We will start this lesson by considering a system of linear equations in two unknowns. Let's have some general remarks about such systems. Thus far, we only solved equations in one unknown or variable. In many cases this unknown was x, but sometimes we used y, but you can also use any other symbol for that matter. When two unknown variables need to be solved for, two equations are required, and these equations are known as the simultaneous equations of such a system. The solutions to a system of simultaneous equations are the values of the unknown variables which satisfy the system of equations simultaneously. That means all the equations at the same time. So you have to find the values of all the different variables that appear, that if you substitute all of them in each equation, it will satisfy each equation of such a system. In general, if there are n unknown variables, then n equations are required to possibly obtain a solution for each of the n variables. Note in general that such a system may have no solution, one solution only, or infinitely many solutions in general. Here we have some examples of systems of simultaneous linear equations, where in the first instance, shown in column number 1, we have two unknowns. Let's say the unknowns were x and y. Note that in such a case we write the equations in such a way that the variables appear beneath each other in columns as indicated on the screen. The next system, of course, is what is known as a 3 by 3 system. 3 unknowns and 3 equations written in a structured way, and also the third column shows a 4 by 4 system. 4 unknowns, a, b, c and d, and 4 different equations, as you can see. All of these are linear equations. Now, for the purpose of this lesson, the focus will be on 2 variables only and 2 different linear equations, and how to solve such a 2 by 2 system of linear equations simultaneously. In the first method of solving a 2 by 2 system of linear equations, we will consider a graphical approach. Here we have the problem: given a 2 by 2 system, 2 equations, 2 linear equations that is, and 2 unknowns x and y as indicated by equation number 1 and equation number 2, we have to find the solution graphically. Now what we have to do is to sketch both of these equations as functions, where we consider in the first case the line number 1 linked to equation 1 as the set of all ordered pairs x, y on the Cartesian plane, where the x and the y must satisfy this particular equation, which is of course equation number 1. And similarly, the graph associated with the second equation will be the set of ordered pairs x, y, if we plot that on the Cartesian plane, where the coordinates x and y, the values, satisfy the equation which is exactly equation number 2 of the system. Now once you have graphed this, and hopefully all of you can graph a linear equation or a linear function, then we have a method where we can solve. Sketch the 2 lines, find the point of intersection of the 2 lines, write down the solution for the system, because that point of intersection will represent the solution for such a 2 by 2 system. And then, of course, test the correctness of the solution by substituting the values for x and y that corresponds to the point of intersection into both equations independently, and check that they satisfy both these equations. So here we have the graph of line number 1 and line number 2. Line number 1, of course, is the graph of the function defined by the equation y is equal to minus x plus 5, if you rearrange this equation. And also the red graph in this case is the graph of the linear function defined by the equation y is equal to 3x minus 3. Now graphically one can find this point of intersection, and if you're very accurate, you'll find that the point of intersection is at the coordinate pair with the x value, or the x coordinate 2 and the y coordinate 3. in this case. So substitute x equal to 2 and y equal to 3 into both these equations, 1 and 2, and that will be the check whether in fact that is the solution of the system. So we see that line 1 intersection with line 2 is given by the singular point set with coordinates 2, 3 for the point in this particular set. And so this is then the solution set, which consists only of one point then, and we know that x is equal to 2 and y is equal to 3 will then represent the solution as we have indicated on the screen. Method 2 for solving a 2 by 2 system of linear equations involves so-called substitution. Let's see what this is all about. Let's have a look at the problem. Solve the following system of linear equations by means of substitution. And the equations in this case are given as indicated on the screen. First equation is 2x plus y is equal to 7. Let's number that, equation number 1. And the second one is 3x minus 2y is equal to 7. The first step with this method is to rearrange any one of the two given linear equations. In our case, we will consider equation number 1 and make one of the variables the subject of the formula. In this case, I choose to make y the subject of the formula, but you might as well redo this problem where you choose to make x the subject of the formula and then just follow the procedure as we will discuss it. So in such a case, if y becomes the subject of the formula, which means we have to transpose the x term to the right hand side and change the sign, and we have then y is equal to 7 minus 2x to start out with. In this case then, we take this as our new equation number 3 as indicated, and the y must now be replaced in our other equation, equation number 2 that we started out with. Everywhere where we have a y, we must replace it with the expression 7 minus 2x. That's the next step. So instead of having 3x minus 2y is equal to 7, we have 3x minus 2 times, in the place of y we have 7 minus 2x is equal to 7. This is the substitution step in this particular process. What follows is just then simplification of the left hand side of this equation by multiplying through with minus 2 into the bracket with the expression 7 minus 2x, and then collect all the x terms on the left hand side, the constant terms on the right, as we saw before when we solved linear equations. We eventually arrive at 7x is equal to 21, divide through on the left by 7 to get rid of the coefficient of the unknown x. We end up with x is equal to 3 as part of this solution for the given 2 by 2 system. The next step involves back substitution, where we go back to equation number 3 or any one of the original two equations, it doesn't matter, and you substitute x equal to 3 into any one of these equations. It's the easiest if you substitute it into the equation number 3 in this case. That's what we did here. And we eventually obtain the resultant y value, which together with x equal to 3 will then represent a solution or a possible solution for the system. So we have x equal to 3 and y is equal to 1 is a suggested solution. How do we check that? We have to take both these values and substitute it into both the original equations and check that it satisfies both equations. Then you can be sure that this in fact is the solution for the 2 by 2 system of linear equations. In method 3 for solving a 2 by 2 system of linear equations, we make use of elimination. So here we have a problem where we have to solve by means of elimination the following system of linear equations. Two equations with two unknowns x and y as indicated on the screen. Now the process in this case involves a strategy where we generate two new equations, say 3 and 4, with one of the unknowns in both those new equations having exactly the same coefficient. If we decide to eliminate the x variable or unknown in this case, then we must make sure that in the new equations that will generate the coefficients of x are identical. This we do by multiplying equation number 1, say, by 3 to have a coefficient 6 for x, and multiplying the equation number 2 by 2 to also have 6 as a coefficient for the unknown x. The rest of the coefficients, of course, will follow accordingly. So the new equations 3 and 4, if we now take equation 4 and subtract equation 3 from it, we will eliminate the x terms, and we'll have a new equation here in one unknown or variable y only. 6x minus 6x is 0, so we have here, if we subtract 3 from 4, that is 9y minus 4y is 5y, 15 minus 12 is 3. So we can then solve for the unknown y in such a case, making y the subject of the formula, dividing through by 5. So y is equal to 3 over 5, but we have to obviously find the corresponding x value, which will then represent a solution for the system. How do we do that? We substitute now this equation number 5, that is the y value, into equation number 1, or into equation for number 2 for that matter. It doesn't matter into which one, but you have to substitute the y value back into one of the original equations, and then if you calculate and solve, make x now the subject of the formula by manipulating the way we saw earlier in this lesson or in this video, then we get the value x is equal to 8 over 5. And clearly we have to check our result in this case by substituting y is equal to 3 over 5 and x equal to 8 over 5 in both these equations and see if they satisfy both of them. And indeed that is the case. So here we have generated then the solution for the 2x2 system of linear equations by making use of the elimination method. I think you're ready now to tackle 2x2 systems of linear equations, and here we have 3 problems for you to solve. In the first instance, given the 2 equations with 2 unknowns as indicated on the screen, you have to solve this using the graphical method. In other words, you have to graph both these straight lines, find the point of intersection. That will be the solution for the system. Secondly, you have to solve the system by using the substitution method. And thirdly, solve the same system using the elimination method. At this point in time, I suggest that you pause the video, do tutorial 3, and then come back and view the solutions. Let us have a look at the suggested solution for problem 1 of tutorial 3. Here we have the system of linear equations, a 2x2 system to solve, and the question is solve this graphically. In other words, you have to graph the straight lines that correspond to the equations as indicated. Now first of all, 3x plus 4y is equal to 39. If you graph this, and you should know how to graph this, use any of the techniques that you have learned in grade 9 or in grade 10 for that matter. Then we have this blue graph, and similarly if we graph the function defined by the equation number 2, then we have the black graph. Now by graphical method, by just working very carefully and indicating the point of intersection, having a look at the coordinates, we see that it corresponds to the point with coordinates x equal to 5 and y is equal to 6. So you can use any method that you know to sketch the 2 lines. You should be familiar with such a procedure. And if x equal to 5 and y equal to 6 satisfies both those particular equations 1 and 2, then this indeed will be a solution. And I'll leave this as an exercise for you to check. Substitute both x equal to 5 and y is equal to 6 into both equations and make sure that both equations are satisfied. So this then, of course, gives us a solution which is graphical for the 2 by 2 system of equations. In problem 2, we have to use the substitution method to solve the same system of linear equations as before in number 1. So here we go. From the equation number 1, we rearrange and make x the subject of the formula in this case to create a new equation, equation number 3. Note that you can also make y the subject of the formula and apply a similar process to solve the system. So in this case we get x equal to 3y over 2 on the right hand side, minus 4 if we divide through by 2 of course, and this must then be substituted everywhere where x appear in the second equation. So there we have it in the first term. So 3 times in brackets 3y over 2 minus 4 gives us, check that, 9y over 2 minus 12 if you multiply out, plus the 4y, and on the right hand side we still have the 39. So that gives us a new equation. Let's say this is equation number 4. Clearly it's one linear equation with one unknown or variable y, where we can now solve, as we did previously in this video, for the unknown y in this particular linear equation. So all the y terms to the left, all the constant terms to the right, divide through by the constant, eventually 17 in this case. We end up, if you solve this, with y is equal to 6. Just check that you also agree with this. What do we do now? Equation number 5, y is equal to 6, must then be utilized to back substitute to find the corresponding x value. Putting 6 back into equation number 3, where we have equation number 3 right here. So we have y is equal to 6 substituted in there, calculate the value correspondingly of x, we get x equal to 5 as before. So exactly the same solution as we had previously with the graphical approach to the system of equations. So here we have then the technique of solving a 2 by 2 system of linear equations by means of substitution. Finally, in problem 3, we have to utilize the elimination process or method to solve the 2 by 2 system of linear equations. Here we have the two equations again, the same system as before in this tutorial. So if we decide to eliminate y, the unknown or variable y in this case, we need to multiply equation 1 by 4 and equation 2 by 3. Why is that? Well, if we multiply equation 1 by 4, the coefficient of y becomes minus 12, and if we multiply equation number 2 throughout left and the right hand side by 3, the second term or the coefficient then of y, the unknown y, becomes plus 12. So all we have to do is to add the two new equations together to get rid of the terms containing the unknown or variable y. And of course you have to then also get the coefficients, resultant coefficients of the other terms correctly as well to form equation 3 and 4 if you multiply by 4 and 3 respectively. So check it out, make sure that you agree with the generation of equations 3 and 4 if we multiply as indicated on the screen. Okay, the next step would be of course to add in this case, because one term is negative, one term is positive with the same coefficient, in this case 12. And we eliminate the y unknown, adding the x terms together we get 17x, adding the constant on the right hand sides of the equations 3 and 4 together we get 85. Make sure that you agree with that. And then we solve the resultant linear equation with one unknown x to get x equal to 5 as before. Now we have to back substitute x equal to 5 into equation 4 or 3 for that matter to then generate the corresponding y value. If we substitute back into equation number 4, that is x equal to 5, then we have 45 plus 12, y is equal to 117. Rearrange again, make y the subject of the formula, solve the linear equation, then hence as we did before, and we get again y is equal to 6. So again, solution in this case, x equal to 5, y equal to 6, and you can in fact test this again by substituting it into both those equations, but we did it before, and this then confirms, if it satisfies both those equations, these values for x and y, that indeed this is the solution according to the elimination process for the system of linear equations. We have come to the end of this video on solving linear and quadratic equations. Remember, consult textbooks for additional examples. Attempt as many as possible other similar examples on your own. Compare your methods with those that were discussed in this video. Repeat this process or procedure until you are confident. Do not forget, practice makes perfect. Goodbye and good luck.